All right, hello. My name is Tom Steepleton. Thank you for coming to my talk. Today I'd like to deep dive on the technology that's drawing the line art images you see on the video here. Not that video, but the other video. It is a graphics technology that was popular for specialized applications in the late 1970s and early 1980s. Unless you had a fortune to spend, you probably weren't going to get high-resolution graphics like this any other way back then. It was a cathode-ray tube, but probably unlike any you've ever seen before. Now, disclaimers. First, because there's a lot to cover and this is only a 30-minute talk, I'm going to speak pretty quickly, but I love talking about this stuff. If there's anything you missed, come find me, and if you want, I'll gladly step through the entire talk again if you want. I'm also only scratching the surface here. I'm only too happy to talk details. Finally, as you can tell, I'm going to be playing from the sheet music. I hope that means I cover all the bases. If this sounds scripted, it is, but for the best, I hope. So, for now, to set the stage, let's talk cathode ray tubes. It's possible that some people watching this talk haven't had much exposure to them. So, around 1870, scientists began exploring cathode rays using devices like this Crookes tube. They noticed that some kind of radiation emanated from the negatively charged electrode, the cathode, of specially made vacuum tubes. If they coated the radiation target with a special chemical called a phosphor, the radiation would make it glow. About 25 years later, physicist J.J. Thomson would confirm that these rays were electrons. And it was handy that these were electrons because electrons have a negative electrical charge and therefore can be deflected by, fittingly, electromagnetic fields. Fittingly enough, in this case, the guidelines show that the effect of placing an old-timey magnet close to the stream of electrons is that their flight path bends. Cathode ray tubes came a long way in the decades that followed. To build up the kind of CRT you'd use for a display, you'd have elements like the following. First, the electron source at the back of the tube, called the gun, would have a heated cathode. More heat makes those electrons more eager to leap forth once voltage is applied. Of course, to have voltage in this case requires a negatively charged cathode to shoot the electrons and a positively charged anode to receive their charge and provide a path for current to flow out of the tube. Most CRTs had a whole system of anodes with several different functions. Anodes that were part of the electron gun would accelerate the spray of electrons and pinch it into a narrow beam, the better for lighting up just a single precise dot on the display. Other anodes, positioned later in the tube, were more for conducting current out of the tube. So here you see the total life cycle as far as current is concerned. Primary electrons eject from the hot cathode. They get accelerated and focused into a beam by the gun anodes. They strike the screen, producing a glow. Then so-called secondary electrons stagger to one of the tube envelope anodes. Negative charge moves from the anode to the cathode. Current flows through the tube. And finally, though they're not shown in this diagram, you'd surround part of the CRT, usually the base of the bell, with electromagnets. This is how you deflect that electron beam so that it lights up the part of the phosphor screen that you want to light up. And here you can see all of these elements in a modern CRT from 1991. Bonus points for anybody who can identify this computer. Right, so CRTs for display in general now, not just scientific experiments, and the problem we face. So lots of people are well familiar with the kinds of CRT displays that draw a picture by scanning the beam across a series of horizontal lines while varying its intensity to make light and dark patterns. This is a raster display, and any sustained image has to be completely redrawn many times a second, since phosphor never glows for very long. This is why CRT TVs and monitors can seem to flicker. Some CRT displays, by contrast, make images by sweeping the beam in straight lines between arbitrary XY screen locations, much like when you play connect the dots on a sheet of paper. The images you get have a characteristic line art style. These are called vector displays, and ordinarily these also require constant redraws, and that can mean flickering too. Incidentally, there seems to be a real renaissance of vector displays here at EMF. Last night, some of you may have seen an enormous vector display projected onto a hill for playing asteroids. That was incredible. And then there's another one, I think at the Edinburgh Hackspace, going on later today for the Elite video game. It's amazing, and so do check it out. But Tektronix Initially, they focused on an older and simpler CRT application, the oscilloscope, a measurement tool for visualizing how a signal changes over time. While the scope sweeps the beam repeatedly from left to right, your signal fed into the instrument directly pushes the beam up and down. If you have a signal which changes in the same way over and over, like a tone, then you can see that repeated change on the screen. This can be very handy for troubleshooting electronics. The problem is that although healthy signals may repeat, glitches often don't. Sometimes there's an electronics malfunction that only happens once every minute or so, a hiccup that knocks the rest of your circuit right out of whack. If you could see what that glitch looks like on your scope, you could fix it, but an ordinary scope doesn't have memory. The glitch will only be on your screen for a blink of an eye before it gets overwritten by an innocuous normal signal. In the bad old days, people tried capturing glitches with cameras pointed at oscilloscope tube displays. Or they fell back on clever indirect means of measurement and deduction. But just being able to see the glitch on the screen would be so much nicer. These days, we solve this problem with digital memory. But back in 1962, that was not an option. Tektronix's solution was to make an oscilloscope screen that remembered what you drew to it. The Model 564 here was the first scope they sold that had one. People found them very useful. At last, they could freeze a moment of time on their screens, trapping glitches for inspection and diagnosis. It was so useful that Tektronix started looking for new nails for their versatile new hammer. Branching out from oscilloscopes, they stood up an entire new division to develop and exploit displays that you only needed to write to once. And computers, and especially computer graphics, were the killer app for this technology. Graphics are incredibly memory intensive. If your display requires you to refresh, then you need memory somewhere in the system so that you can draw what's been drawn before. If you can eliminate that requirement, you can save thousands or tens of thousands of 1970s pounds on your unit cost. For this reason, between about 1975 and 1983, computers and terminals with tech display technology offered some of the highest resolution graphics around. On the screen, you can just see how, in the course of the development, they basically got bigger and bigger, starting with something with like 9 or 10-inch displays, going all the way up to this 25-inch diagonal behemoth on the bottom right. But take note of the 4054A in the top right corner with its 19-inch screen. I don't have one of those here. It weighs like 90 kilos, so it would be too hard to bring. Oh yes, sorry. But how did it work? Some of you may know, but for everyone else, take a moment to imagine what the mechanism could be. I don't think you're going to guess. I just want you to think ahead and see if the solution tech came up with is wilder than your expectations. As you're pondering, I'm just going to put up this video of how I've been making some of the animations you've been seeing in this presentation. The computer is actually that Tektronix 4054A from a photo on the last slide. And you can see that I draw the image, the camera in front down the bottom part of the picture snaps the photo, and there you go. And you just do this for hours. And now Linux will not let me advance the slide yet, but we just have to wait. So keep imagining. Ah, yes, okay. So, are you ready for the secret? So stand by for a kind of TLDR in 3, 2, 1. The tube has more guns. And unlike the focus beam of the right gun that draws the image to the display, these new flood guns, they douse the screen in a big gentle shower of electrons. We're constantly bathing the screen in energy. Obviously, this has something to do with how the screen can store an image. But it's this curve which is the real TLDR. If you understand this plot, you'll understand the physical reason for why the screen stores images. It all has to do with what goes on the faceplate of the tube, which, to a first approximation, is a big sheet of glass with a phosphor coating on the inside. And that is basically a big insulator. That means charges can build up on different parts of the faceplate. Electrons that get shot at the faceplate can get stuck there, for example. Stuck as in maybe static electricity. So now we know that because electrons have the same charge, they will repel each other. And conversely, if there's a non-conductive surface that has a positive charge, it will attract a negatively charged particle. So now we can start to take a closer look at the things that can happen on the faceplate under the mild, steady barrage of the flood gun electrons. If a small neighborhood of the faceplate has a certain concentration of positive and negative charges, which is a different way of saying that it has a certain voltage relative to the flood gun cathode, then you get a situation like this. The electron strikes it with some mild force, which is not really enough to activate the phosphor. Nearby electrons on the faceplate are repulsed, perhaps including one with enough energy to escape the faceplate and wander off into an anode. So in reality, this cartoon is a bit more characteristic of flood gun electrodes. Of course, however, real life is messy, and so sometimes the mixture of charges on the faceplate isn't perfectly balanced, like in the example shown on the last slide. If the faceplate target is rich in negative charges, then the flood gun electron will be repelled. It simply won't contact the screen at all. But this situation isn't sustainable. Eventually, the concentrated electrons will dissipate from the surface, raising its voltage back to something more reasonable. Conversely, if a patch of screen is slightly positive, then the flood guns will simply fill in these small gaps. You may not have realized it, but we've been describing the self-reinforcing dynamics of this part of the curve boxed here. The balance condition that we showed in the first animation is point G, where the x-axis is the voltage level, and the y-axis describes how many electrons come out for every electron that goes in. Note that G is at a y-axis value where delta equals 1. For every electron that goes in, one more comes out. In the voltage interval surrounded by this box, the system has a feedback mechanism that always pushes the voltage and current back to point G. And critically, the flood gun electrons can never strike the screen with enough intensity to make it properly glow. So if you like, we could call this interval of stability the regime of darkness. Just to lock this in, let's return to the animations. In the first one, we're right at the stable point. Delta equal 1 means 1 electron in, 1 electron out. And in this scenario, the extra electrons mean a more negative voltage, so to the left of G in the plot, the electrons dissipating are bringing us back to the stable point. While this happens, delta is greater than 1. More electrons leave the target than approach it. And conversely, up to a point, the screen can restore itself if bits of it become too depleted of negative charges, if it gets too positive. Flood gun electrons will nestle into places that lack other electrons, again, up to a point. But what about the rest of the curve, over to the right of point A? To find out, we're going to need to strip off a lot of electrons and make a part of the screen really positive. Okay, here we go. This isn't really how it works, of course, but however it happens, notice that we now have a big swath of the screen that is a lot more positive than it was. And this brings us to a second separate interval of stability centered around point P. Flood gun electrons that strike parts of the screen with these higher positive voltages will do it with enough energy that it triggers the phosphor and causes a glow. So let's call this the land of light. Why not? Here's the kind of thing that happens here. Actually, it's three things. First, a more positive faceplate draws the flood gun electron towards itself faster. Next, because the impact is so energetic and penetrating, it ejects 2 secondary electrons, not just 1. It makes this part of the screen even more positive, and that's important. And finally, as mentioned, the energetic impact causes the phosphor to glow. That last animation shows us what happens roughly at point M, and you can see how it nudged the faceplate target toward even more positivity in the direction of point N. And once you go even further than that, even that patch of the faceplate gets so positive that even these high-impact primaries can't knock anything loose. They still make the screen glow, though. So that's what this curve means. There are 2 intervals of stability that can be achieved on any part of the faceplate. That's how storing works. Why this is a bistable storage tube. Dark parts stay dark and light parts stay light. And because it's all happening on an insulator, those areas don't mix or move around. A dark patch on the screen can be immediately adjacent to a bright patch, and provided your screen is correctly calibrated, as Tektronix put it, remember they're an oscilloscope company, then they'll never mix. So how do you make something go from dark to light without a bulldozer? Instead of that, it's a good old-fashioned higher energy electron beam shown here in this Tektronix conceptual diagram of how the tube works. This must be for an oscilloscope because it's only 2,000 volts. On a 19-inch display, it's actually 6 kilovolts. Here you can see us measuring it very carefully. But by big screen standards, this actually isn't all that much. A Raster CRT of comparable size would probably be well in the 5 figures. Anyway, here's what this mighty right beam does. This one's got a new curve, and you don't really need to look into it. As you can see, it just shoves whatever piece of that, it's right on top, it's huge, it's very powerful. It just shoves whatever piece of the screen is in its path up towards the second stable point. And as it does, the beam really lights up the phosphor. That's why you can see a bright dot. In fact, if the right beam dwells on one spot long enough, it can actually damage the screen, burning a little hole in the phosphor there. That's why if you see a stuck beam on my terminal installation over in the lounge, I need you to press this red button and call me. So please do that. Tektronix liked this marble analogy to explain how the bistable behavior in this tube worked. The marble will always roll toward a stable point. You can see that there are 2 of them, so it's a bistable system. When I say they liked the marble analogy, I mean I think they really liked it. So this is Bob Anderson, the engineer at Tech, who did a lot to develop their storage tube technology. When I saw this picture of him, I couldn't help but notice this object on his desk. Now, it appears that this is lost to time, and I haven't found any resource that talks about it, but you can find it in multiple pictures of Bob. So I think it must have been important to him. Now, there's one last thing about how this tube works that we haven't covered, if you can actually believe it, and that is erasing the display. Once you've got stuff on the screen, how do you take it off? And here I've got some disappointing news for you, I'm afraid. And one of the main reasons you just stop seeing these things after about 1984 or so. You can't just erase part of the screen. You have to erase everything. And when you do, you see this quick double flash. It's frozen in time in this image where you can see the pattern of the big 19-inch display's dozen-plus flood guns bathing the screen. Here's what it looks like in real time, and watch closely because it goes pretty quickly. It'll do it again. Yeah, that's it. So I ran out of time to make animations to explain what's going on here. So as a substitute, I'm going to try to make this voltage over time graph come to life for you with sound effects. Please prepare yourselves. So it all begins on the left-hand side when the target voltage is raised to 150 volts. Electrons drain from the faceplate. Flood gun electrons go zip and impact vigorously into the draining, newly positive screen, flashing it green like we've seen. Then, boom, the target voltage body slams down to flood gun voltage. Electrons flood back onto the faceplate via capacitive coupling. Some from the flood guns tube build like snowflakes as the voltage is gently raised back to the normal operating level. Then it all happens a second time. If the first one didn't clear the screen, the second one sure did. Now some of you might be wondering, hey, what do you mean by change the target voltage? I thought it was an insulator. Well, yes, the phosphor is. Now, a lot of my talk has been schematic in nature, overviews of how the mechanism works without highlighting specific features. This is a good opportunity to do a little of that just once, to show just one of the amazing details the engineers had to invent to really make this screen work. Here it is. It's a cathode-ray storage tube having a target dielectric provided with particulate segments of collector electrode extending there through. You see why I needed notes. Folks, there are thresholds in life, and I want to usher you now to the time in your life when you knew about a cathode-ray storage tube having a target dielectric provided with particulate segments of collector electrode extending there through. What does that mean? Well, the faceplate isn't just a piece of glass with some phosphor on it. I was oversimplifying earlier. It's actually an exotic pizza. Layer 50, that's the glass, but 52 is a thin coat of conductive clear material, indium tin oxide. Your phones use the same stuff for their screen circuitry. Then 54 are these teeny tiny cobalt cones that poke through, the phosphor. Cobalt is conductive, and critically, it's optically dark. Folks, this is an anode. The faceplate has a built-in anode. Secondary electrons can escape the phosphor and disappear down a nearby cobalt cone and right out of the display. Here's another diagram, one that shows something a little bit closer to the geometry of the big 19-inch tube, and here it is to scale. The process for making this a nearly microscopic structure is described in the patent, and it's really wild. but I'm going to skip that here. Now, if you look really, really close at the lines of a DVST computer display draws, I think you can see where the cones are, those little black dots. All right, they've invented it, and now the product. So I don't have many pictures of a DVST on its own, so I pulled this one from a brochure. Smaller tubes like this one, and same as this one here, have a flat faceplate and a ceramic bell. I suspect this person worked in the information display division, but I don't really know. And here's a repeat of that family photo of some of the many displays in computer products where tech incorporated these displays. Don't forget, there were lots of scopes too. I'd love to tell you where people use these things. The answer is mainly places where you needed high-resolution line art graphics on the cheap, so university science labs, US Navy submarines, but there's not much time. I also can't really go into how these things faded away. The TLDR is that computer memory got cheap, and people wanted animated graphics, which you just can't do. Instead, I'll highlight the storage tube's zenith in the popular spotlight, which was on the original 1978 television series Battlestar Galactica. And boy, they were really excited about this in the Tektronix internal newsletter. Here's an image of the Galactica bridge, and like any self-respecting starship, there's a whole lot of techno features for the crew to poke at as they battle the Cylons and attempt to find Earth. But if you look closer, it's all Tektronix 4051 desktop computers. Always has been. The machines were convenient for filming. You didn't have to worry about synchronizing the shutter of your camera with the screen refresh because there is no screen refresh. But Tech actually got a brilliant product placement deal here. It wasn't just the computers. A lot of the blinking light thingies are Tech test equipment. The LA field sales representative knew what they were doing. I'm not sure how much this earned in actual Tektronix sales, though. As long as we're on Battlestar Galactica, I'm going to indulge myself and show the kind of animated line drawing that the display just seems to be perfect for. This is what I was animating in that image earlier. This is a modern graphic derived from an STL file on Thingiverse. Some of you may be reminded of the Star Wars scene where they're briefing the attack on the Death Star. That didn't use these scopes, but it's a similar aesthetic. Okay, one final aside. When I advertised this talk, I promised to swing by some early uses of storage tubes, particularly computer memory. I don't like to break a promise, so here we go. Devices called storage tubes, which were also called Williams tubes, really were used for computer memory, but bit patterns were represented as accumulated charges on the faceplate of a CRT. Here's what one of these tubes looked like at the National Museum of Computing. Now, I'd long thought that the storage tubes had a similar construction to the DVSTs that we've been looking at, but no, they don't have flood guns, and they have to be refreshed like regular CRTs do. The patterns of the bits on the screen would look something like this, and it's read in a manner that makes use of secondary electrons in a way that you might be able to think about now. So check it out later maybe, and sorry for the tangent. It's my fault for getting confused by how the term storage tube is overloaded. One of them stores images, the other is part of a bigger mechanism that stores data using a more ordinary CRT. Now, as a final item, it's not too easy to get your hands on your own direct view storage tube device these days. The youngest ones are about 40 years old, and they weren't useful for much once they were obsolete. Most of them were pretty well used. But these things used to be fairly common in university and industry computer labs, the kinds of places where they were developing things like Unix and the X window systems. And so if you're a Linux or other Unix user, a simulator may be closer to hand than you realize. Some of you may have it installed on your laptop right now. Many of you will have used it already at some point in the past. It looks like this, and here's the command. It's just Xterm. Xterm is a really old terminal program these days. It's sort of the original for the X window system. Most people use GNOME terminal or whatever, and on my distro it wasn't even installed by default, but if you do have it, you only need to add the -T flag and you're in Tektronix mode. The behavior of the real thing is emulated with fairly high fidelity. The font isn't quite the same, but just like on the real thing, the delete key can't actually erase any characters because it's pretending to be a storage tube. For higher fidelity, make sure you select the right colors for your display. Once you've got this, you can just start piping Tektronix graphic commands to the screen. For more info on how to do that, just come find me. I've got some code on my GitHub. But there's something about the real thing. These tubes are so fascinating to me, and the way they draw really captivates. Although the computer displays were designed or intended for high-tech digital systems of the era, you can just feel the carefully balanced analog nature of the system right beneath the surface. Few things exemplify this more than how the 19-inch display behaves when you cut the power. The right gun gasps and the flood guns wink and slowly fade away as the image turns into a liquid, then evaporates. So just watch this. Okay, we'll do it again. All right. And with that, that's a good note to end the talk on, I think. Thank you all so much for watching, and thanks also to these people and the organizations on the screen. As I mentioned at the beginning, I've only just scratched the surface today, and I love to talk about this stuff. So come find me if you're eager for more. And if you want to see one of these tubes up close, you can visit this terminal in the lounge through afternoon on Sunday. Thank you all once again.